So my next step or next question is, does this set of code words along with the operation of XOR, what is the XOR operation? Bitwise XOR. It is, you can also think of it like binary addition or addition modulo 2, not binary, addition modulo 2. Addition modulo 2 means 1 plus 1 will be 2 and 2 modulo 2 is 0. All other case is very simple, so this is 0. All other cases are very simple, right? This is addition modulo 2. So does C comma addition modulo 2, does it form a group? Is it a group? Now why are we checking random things to be groups or not? Like, we understood the concept of code words, we understood that we are introducing additional bits in a message so that any error detection and correction can be done. But why are we checking anything under the sun to be a group? Basically, as I said, we have to be able to easily detect for huge messages, right? For example, even if you just say hello world. Hello world has 11 characters, and 11 characters means 88 bits minimum if you assume each character is 1 byte. And if you take ASCII, if you take Unicode characters, then they are even bigger. So basically there is huge amount of data, and to process the huge amount of data, to find any errors and to correct any errors, we usually take the help of generator matrix G. G is a generator matrix. Generator matrix is used to represent the code, and there is a parity check matrix H. Parity check matrix, which is used to check the parity of the bits, even parity, odd parity, and accordingly whether the message has any errors or not. So given these two, like these two matrices will be useful only if the set of code words that we have along with the addition modulo 2 operation, which is the XOR operation, they form the group. Okay, so that's why we are checking whether it's a group or not. So you know the steps for checking whether it is a group or not. What is the first property that we check? I hope you are solving along with me. Closure. So how do you check closure reliably? We have 4 code words. We can check whether every pair of code words, so 4C2, basically there will be 6 pairs, but along with that we can also do it using a multiplication table or a Cayley's table. Okay, so we'll do the Cayley's table, which is also called as multiplication table or composition table, and these are our code words. Okay, now what is the basic property of XOR? XOR of any number with itself will always be 0, because when both the bits are the same, XOR value is 0, and when both of the bits are different, the XOR value is 1. Okay, so there are two basic properties that we have to take care of, that is x XOR x. For any for any number x, it will be 0, and any number XOR 0 will be that number itself. Okay, so by the second property you can say that we can easily fill this row and this column. Okay, we can also fill the diagonal easily. All the diagonals will be zeros. Okay, and then for the remaining ones we'll have to do the calculation. So 0 1 0 1 1 0 1 0, all the bits are different at different positions, so it will be 1 1 1 1. 0 1 0 1, and these are all ones. So basically wherever there are ones we will get zeros, it will be complemented, right? And 1 0 1 0 again complemented. Okay, and because it's symmetric, here we will get this, right? So that is our multiplication table or Cayley's table. And from the values in the table, as you can see, all these values are within the group of the keywords or the group of the code words that we have. So therefore we can say that this is closed. Secondly, let's check for associativity. XOR is associative. Okay, if you have three numbers x, y and z, no matter whether you perform x XOR y first and then XOR z, it will always be equal to x XOR y XOR z. You can try with any example. Let's say 0 1 0 1 1 0 1 0 and whatever 1 1 1 1. Okay, so if I perform XOR of these two first, I will get all ones, and all ones XOR all ones, the answer will be 0. Now if I perform the second one first, that is 1 0 1 0 XOR 1 1 1 1 first, the result will be 0 1 0 1, and 0 1 0 1 XOR 0 1 0 1, the answer will be 0 again. So you can say that it is equal and therefore it is associative. Then you will look for inverse. Now, okay, before inverse we'll have to look for identity. Okay, so identity for XOR will be 0, as we had said x XOR 0 is x, so any number XOR 0 will be x, so 0 is the identity. So we have reached the monoid stage, and then we have the inverse stage. So for inverse we will observe where in each row we have zeros. Moreover, from this we can observe that every number is inverse of itself. Every x is inverse of itself, right? So inverse, it's a self-inverse, or you can say inverse of itself. Every number is an inverse of itself, so therefore we can say that it is a group. And bonus thing, x XOR y is the same as y XOR x, therefore we can say that it is an abelian or commutative group.